Hello, everybody. This is the lecture for section 4.3, maxima and minima. So we're going to continue on our study of applying the derivative to different things in math. So this is, like I said, chapter 4 is nearly entirely application. So the next one that we're going to do is this right here, maximum and minimums. Okay, so we know what a derivative does. It's the instantaneous rate of change or the slope of the tangent line, right? That alone can let us find a couple things of how a graph behaves. And that's what we're going to be studying for the next couple of sections here, okay? So what I want to do first is define a couple things. Let me scroll down a little bit. Let me scroll down so I can get, there we go. Okay, so the first definition that I want to do is this definition of an absolute maximum and an absolute minimum. Okay, and it's exactly how you think it is. Okay, so let's say you had a function that's defined over an interval, right? An absolute maximum is basically the very tippy top, and the absolute minimum is the very bottom, right? So if you had a function, it doesn't matter what it looked like, right? So if you had a function that did, something like that, right? And let me just go ahead and take, a similar one, right? So go ahead and do, right? Absolute minimum would have to be this point right here, right? Because it's the lowest point out of all of the points that are there, right? And then same thing for absolute maximum, it's going to have to be this point right here, because that's the highest. So it's like the definition says, it is an absolute maximum at x equals c. So this value down here is going to be x equals c for both, right? If f of c is less than all other f of x, right? That's for the minimum. And if f of c is bigger than all of other f of x, and that's going to be for the maximum. Okay, it's that simple. Okay, the next definition I want to give is that of a local maximum and local minimum, which isn't too far different. So what I'm going to do is I'm going to try to replicate the graph that's above. So squiggle, squiggle, dip, squiggle, and it keeps climbing. And then in the other one, same thing. It's going to have one big hump, and then it's going to have two little troughs, and then another nice hump. There we go. That's good enough. Okay, so the definition of a local minimum, right, and a local maximum, okay, is basically the same idea, except it's just another hump. It's the highest over a small little bit. That's it. Okay, so we know that for these, right, these are your absolute max and mins, right? But we can consider these other points. So this other little dip right here, this other little dip right here, this little dip right here, this dip right here. Those are all called local minimums. Okay, that is, I can draw a little sort of let me go ahead and do that. I can draw a little interval around that point. That makes any sense right there. There we go. Another one, another one. I can draw a little interval where over that little interval, it is the smallest value, okay? As opposed to the other one, as opposed to, this point right here, where it is the absolute smallest value for everything, okay? And then likewise for the absolute maximums, right? So this is my local maximums. This is the absolute maximum, but this can be considered a maximum. This can be considered a local maximum. This can be considered a local maximum. Okay. It's not the absolute highest point, but it's, it's got a little hump there. It goes up and then comes down. Okay. Okay. So what I want everybody to do now is, I think the next thing that comes up is some quick checks. It says use a graphing utility. Please just use a graphing utility. Okay. The reason why is because I'm going to make you guys do the actual computations for how to find these later. So a lot of these, the submissions for this quick check are going to be more than likely Desmos calculations, and that's perfectly fine. Okay, just showing you guys how to find maximums and minimums. That's it. Okay, so now what's going to come up is a couple theorems and a couple definitions, okay? The first one is what's called the extreme value theorem. That's pretty helpful in what we're going to do at the very end with the location of absolute extrema, okay? Let me actually scroll down so we can get at least... Hey! Bronx, stop it. Oh man, that scared me. Okay, back to this. That was the mailman. And as always, all dogs hate mailmen. So, okay. So let me go ahead and do theorem, the very first theorem, the extreme value theorem, okay? So let me read it out first. If f is a continuous function over a closed bounded interval AB, then there is a point in AB at which f has an absolute maximum and a point where f has an absolute minimum, okay? So I like pictures, okay? So it doesn't matter. It doesn't, for this graph, it doesn't matter where it starts or where it ends. It doesn't say that here, right? So I'm just gonna draw an XY, right? That's my Y, that's my X. I need to draw a continuous graph, and I'm gonna choose my AB first. Let me choose my AB first. So here's A, and here's B, right? I get to choose my continuous function. You can do whatever it wants, right? Let me make it a little bit more pronounced. So continuous function. Okay. According to the theorem, it says that there exists at least one point, there must exist a point where it attains its absolute maximum, and there must exist a point where it attains its absolute minimum. Okay. So what this theorem does is it guarantees us these two values. That's what it does. It guarantees us these two values. That somewhere over AB, over our interval AB, over this interval right here, over that interval, you're going to have your absolute maximum and you're going to have your absolute minimum. Okay. So the next definition is one that we're going to be seeing a lot of from here on out. It's that of a critical point. So a critical point is where the derivative is equal to 0. So thankfully, I've made you guys do this a lot already. So the critical point is where it is equal to 0, or if f prime of c is undefined. So basically where you break math, where you, let's say you take the derivative and you end up dividing by 0, or you end up taking the square root of a negative, okay? So those are where f prime of c is undefined, okay? Wherever that happens, we call that a critical point, okay? The next theorem, Fermat's theorem, states as such: if f has a local extremum at c and f is differentiable at c, then f prime of c is equal to 0. So basically saying that if you have any extrema, either a maximum or a minimum, right, and your function f is differentiable, then you have that the derivative is going to be equal to 0 at that point, okay? All of this, right, is, so this next theorem right here, location of absolute extrema, this is the culmination of everything that I just said, the couple definitions from above and the couple theorems that we did above, okay? So let f be a continuous function over a closed bounded interval AB. Then the absolute extrema of f over I must occur at the endpoints or at the critical points of f over I, okay? So let me go ahead and draw the picture again. I've done sort of this picture already above, but it's got a little bit of a different, it's got a little different sort of finale, different consequence here. Okay, so f be a closed, a continuous function over a closed bounded interval. So I'm just going to go ahead and draw a squiggle, right, over AB, and this is my A, and this is my B, right? then what this theorem states, the theorem of the blue, location of absolute extrema, is that it states that I am guaranteed that the absolute extrema, maximums or minimums, of this function either occur at the endpoints, so right here, or the critical points of C. So, or right here, and right here. Okay, notice how the endpoints, these points right here, they're endpoints. They're going to have values. They may or may not be bigger than anything that's already on there, right? And then there are these values right here where the derivative is equal to 0 because they are critical points, aka the slope of the tangent line is 0, right? That's what all of these theorems and all of these definitions give us, or at least all the theorems do. They are guaranteeing us specific values, okay? So in this last theorem that I presented, then we are guaranteed, if we have a continuous function over a closed bounded interval, okay, then we are guaranteed that the absolute extrema, either the maximum or the minimum, has to occur either at the endpoints or at the critical points of f over I, okay? This altogether gives us a pretty good game plan for how to find local extrema for our function, okay? And those are these three right here. So first one is just straight out, first of all, find the values of the endpoints. That's number one, okay? Number two, find all the critical values, wherever those critical values are, okay? And then number three, compare all the values that you found for number one and number two, okay? The biggest one is your maximum and your smallest one is your minimum. That's it. Okay, so let me go ahead and do this example right here really quick for everybody, okay? And actually, I want to frame up the 3 steps that we got. Farther down, there we go, almost there. Oh, all right, so let's go ahead and start doing this one. So we have a function here, okay? Believe me for now, this is a continuous function. You don't have to worry, okay? Over -5 to 5. Make sure to provide coordinates for each and specify each point as a maximum or minimum, okay? So the first thing I'm gonna do is number one, just find the values at the endpoints, okay? So what I'm gonna do is I'm gonna calculate the values for my endpoints. That's gonna be step one, right? So I'm gonna do f of my first endpoint, -5, right? So this is going to be -5 minus 1 over -5 squared minus a -5 plus 1. And if you compute this out all right, you should get -0.1935 change, okay? And that should come out to, if you did it by a fraction, I believe that is -6 over 31, okay? Number two, or sorry, before we go there, f of 5, right? I'm gonna do 5 minus 1 over 5 squared minus 5 plus 1, okay? And that comes down to same sort of value, 0.19, 0.47, which if you kept it in the fraction form should be about 4 over 21. Okay, so I'm gonna start highlighting these values here, this one and this one. Okay, part 2 says find all values, all the critical values, right? So that means number 2, critical values means I need to do f prime of x equals 0, okay? So we know that our f of x is going to be our x minus 1 over x squared minus x plus 1, right? So we have a high and we have a low. Okay. So then let's go ahead and start taking derivatives so we can use the quotient rule. H prime, whoops, sorry, H, let me separate them out first, is the x minus 1. Low is the x squared minus x plus 1. So H prime is 1. Low prime is 2x minus 1. So therefore, f prime of x is, we get to follow our quotient rule here. So it's the low x minus 1, d high, whoops, low, aha, low x squared minus x plus 1, d high times 1 minus high x minus 1 times d low, which is 2x minus 1 all over the bottom squared, x squared minus x plus 1. Okay, and if we clean this up a little bit, we should get something along the lines of f prime of x is equal to minus x squared plus 2x all over x squared minus x plus 1 quantity squared. So we have our derivative, right? We have our derivative. Okay. Now we need to find where this thing is equal to 0. Okay. We need to find out where this thing is equal to 0. So the first thing I'm going to do is determine where this thing is undefined. So that means maybe we might divide by 0 here. So when is x squared minus x plus 1 equal, actually, let me do this. So f prime undefined first. Let's go ahead and find those first. Right? So this would be undefined if the bottom is equal to 0. So x squared minus x plus 1 equals 0. The only way we can do this is by quadratic equation. So minus 1 plus or minus the square root of b squared, so minus 1 minus 4ac 1 times 1 all over 2a, which is times 1. Okay? And it's supposed to be minus a minus. That's my bad. Yep. So then here we get 1 plus or minus the square root of minus 1 squared, right? Minus 1 squared, that's 1, minus 4, that's going to be a minus 3 all over 2. This automatically tells us, this right here in particular, says we don't have answers for this. Since the determinant inside is not positive, we know that this is never going to be 0. So this automatically tells us all values are defined. So f is undefined nowhere. Okay, so that's part 1 of our the critical values. Okay, so now let's do f prime equals 0. This is the next portion, right? Okay, for this one, okay, we're going to look at this derivative that we have here, right? And we're going to take a look at when this thing is going to be equal to 0. So now this requires a little bit of a sort of like an algebra trick that you guys are going to have to get comfortable with, okay? Suppose you had, I'm going to explain it down here. Suppose you had an a over a value b, right? And it's equal to 0. Suppose you had a fraction that is equal to 0, right? The only time this is possible, right, is if a is equal to 0. If b is equal to 0, then the value is undefined. We already did that. okay? So the only way that a fraction is going to be equal to 0 is if only the top is equal to 0, okay? So then that's all we got to do. So minus x squared plus 2x in our case has to equal 0, right? That top thing, we can go ahead and factor stuff out, right? So I'm going to do this. Minus x minus 2 is equal to 0. Okay, this gets us that either x is equal to 0 or x is equal to 2. These are our two critical values right here. Okay, we're not done yet. This is still step 2. Okay, this is still step 2. So what we're going to do now is we are going to, am I doing this off of? Yes, okay. We're going to plug these two values into our regular equation. We're going to plug these two values into our regular equation. So we're going to do f of 0. That's going to be 0 minus 1 over 0 squared minus 0 plus 1. That is going to be minus 1 over 1, which is negative 1. F of 2 is equal to 2 minus 1 over 2 squared minus 2 plus 1. And that's going to be 1/3. So let me actually, before I mess everything up here, I'm going to highlight these values. Okay, so now we're done with step 2. So from step 2, we found the critical values of f of x, right? Found the critical values of f of x and determined the values at those points. Okay, if you recall from the theorem that was presented right before this, right? Then what the theorem stated is that our extrema must exist at either the endpoints, these two right here, right? Or at the critical values. Which we just now found at the end of step 2. So now all that gets to happen is we just get to decide. So step 3 is basically comparing all of our values from step 1 and step 2 and seeing which one's the biggest and which one's the smallest, okay? So to do that, I'm just gonna collect the values here, right? So f of 5 is 4 over 21. F of negative 5 is negative 6 over 31. Okay. F of 0 is negative 1. And F of 2 is 1/3. Right? So now, our biggest one, is the 1/3. And our smallest is the negative 1. So that's all I get to do. I get to compare them. So that means our max is at, our max is at 2, 1/3, and our min is at 0, negative 1. And that is it. This is our final answer right here. Boom. Okay. So notice how I played down the 3 steps, the 1, 2, 3 that was above. Okay. Keep a track of your thoughts here. It probably will be really useful for you to like go through the steps 1, step 2, step 3. okay? Next thing up down here is quick checks. So these are quick checks from the problems from above. So if you were odd or if you were even, you should know through your graphing utility where the maximums and minimums of these are, right? Just by looking at the graphs, okay? In this step, in this quick check, you are actually going to do the steps 1, 2, and 3, okay? And they should line up to the problems that you had up before, okay? So try them out. Give them a shot. I'll be looking at the answers and posting them up in the notes a little later, okay? And then after that, it's lecture questions. If you got questions on these, please let me know. Stop by my drop-in Zoom hours from 3 to 6. Besides that, I'll see you guys around. Cool.